previous video in this series, we learned how, when you're given the magnitude and direction of the overall vector, we learned how to figure out the components. Now we'll learn how to go in the opposite direction. Given the components, we'll learn how to build up the overall vector. This is a very important skill for your physics class. Your professor assumes that this skill is easy for you, so we need to practice this until we get to the point that it's boringly easy. This is not supposed to be the hard part of physics. Well, here's the first skill that we'll need. Pause the video and see if you can do this. Okay, well, here's how to do it. So one way we could do this, so the important thing is to keep in mind that the components here are themselves vectors, and the components represent the overall vector. In fact, as I briefly mentioned in the first video, the components should add up to the overall vector. So for example, if I take this component, how would I add then? How would I add this component? Well, we use the head to tail method. Where the x component ends, that's where our y component is going to begin. Okay, and then we'll copy this, and we'll simply put it where the wx ends. That's our head to tail method, where the head of the first component is at the tail of the next component. And then w would be the sum of these two components. So can you draw w? You might want to pause the video and see if you can draw w here. Well, w, the overall vector, should begin where the first component begins, and then end where the second component ends, like so. Whoops. And then where's the arrow on w? Well, we want the tail of the overall vector where the tail of the component is, over here. And then since there's the head of the component here, there should also be a head for the overall vector. Or we could say that the components point left and to the right, so we want the overall vector. Excuse me, the components point up and to the right, and therefore we want the components to point up and to the right. Now, very important to label this side. What's this? This is our w vector. Okay, so that's the skill of drawing the overall vector from the components. Now, of course, there's a different way we could have done this. Instead of drawing wx first, we could have started with the wy vector. Then we could take the wx vector and have the wx vector start where the wy stopped. And then the overall vector would start over here and end over here. Oops. And it would point up and to the right again, because the components point up and to the right. So that would be the w vector, and this over here would be wy, and this would be wx. And I hope you can see that this vector is the same as this one, so that gives us two ways to get the same vector. In fact, I'll just show you one more way that we could do this, just so that we're really understanding. We could take the wx vector, and then we could put the wy vector over here at the tail of the wx. So this would be wx, and this would be wy. Then we could draw another line here parallel to the wx vector, and another line here parallel to the wy vector. And that rectangle that we formed, the diagonal of that rectangle, this diagonal would be w. and the components point up and to the right, so W would point up and to the right. We could say that this is the W vector. Now, of course, on a real problem, you don't have to do it 3 ways. You can just pick one of these ways. And you can pick whichever way seems most convenient for the problem that you're working on. I think for our purposes in the introductory class, making the right triangle, using the right triangle approach will usually be the best approach. So I think one of these 2 methods is usually best, but you should be able to see that all 3 methods gives us the same W vector. Okay, so now we've gotten the answer 3 different ways. Okay, so now we've learned the skill of drawing the overall vector from the components. Remember, what we're trying to go over here is if we're given the components, we want to be able to get to the overall vector. And that's what we did here. We were given the components and we were able to draw the overall vector. Remember that wherever you have the tail of a component, you should also have the tail of the overall vector. And where we have the head of the component, we have the head of the overall vector. So for example, in this case, we have all 3. Here we have the tail of the overall vector, so we also have the tail of each of the components at that point. Well, please pause the video and try this problem. Well, first we take one of the components. It could be either the x or the y, and we copy it. So I'll take the x component. Then we can take the y component and copy it. And we want, I'll use the method where this vector ends, where the first vector began. Excuse me, this vector begins where Vx ends. And then the overall vector starts over here where the first vector started and ends over here where the last vector ended. Since the components are left and up, the overall vector should be left and up. Here we have the head of the component, so we also have the head of the overall vector. And here we have the tail of the component, so we also have the tail of the overall vector. It's always important to put in some helpful labels. So what's the label here? Well, this is the overall vector side, V. And these are the components. Okay, and we know there's 2 other ways we could draw this. Instead of drawing Vx first and then Vy second, we could have copied Vy first and then put Vx at the end of Vy. Or we could even have used the rectangle approach where both Vx and Vy start in the same place, and then we use reference lines to draw a rectangle. So if you want, you can try all those other approaches as well. Each approach that you do, though, should give you an overall vector that points up and to the left. From these components, you should get an overall vector that points up and to the left. Pause the video and try this problem. Well, now we'll go through it together. We're given the components. So we know that the x component here is -4 units. And the y component is +7 units. The problem didn't mention a sign for the y component, but we know the convention in math is that if there's no sign, you assume the number is positive. So we assume this is a +7. And we know that we've talked about how for beginners it's best to include a positive sign in front of positive components. But you can't expect the problem to do that. So we're not surprised that the problem didn't include that plus sign, but we should put in that plus sign ourselves. That's just a good habit for beginning students. Why is that a good habit? Well, for one thing, that emphasizes that we know the direction of this component. The direction is up, because it is in the plus direction, which is up for those axes. And this negative x direction would be left. So we know those directions, and we can draw arrows to represent ux and uy. So the magnitude here is 4 units and 7 units. Magnitudes are never negative, so there's no need to include the plus sign to emphasize that these are positive. Okay, now what do we do next? Now we want to figure out the overall vector. Well, this is 7 and this is 4. Does that mean that the overall magnitude is 11? Or maybe we should do 7 minus 4, so the overall magnitude is 3. Can we just add these two components? Well, no, that doesn't make sense because they're not pointing in the same direction. Since they're not pointing in the same direction or even in opposite directions, you can't just add these two numbers. Instead, we actually have to draw the overall vector. Well, we have a ux of negative 4 units, so that goes to the right. Maybe like so. And then uy, positive 7. So where ux ended, I'll draw an upward arrow of 7. And notice I'm not going to get this perfectly to scale, but you should certainly draw this arrow longer than this arrow because this magnitude is bigger than this one. And then where's the overall vector? Well, the overall vector starts over here and ends up here. I'll do my best to draw a straight line, and it points in this direction. The components point left and up, so the overall vector points left and up. Where there's a tail of the component, there's the tail of the overall vector. And where there's the head of the component, there's the head of the overall vector. And we should label this side as our side u. So now, what do we need to do? We need to get numbers for the length of this side, which represents the magnitude, and we also want to figure out the direction. And we know that we can indicate the direction of an overall vector with an angle. And I think the most convenient angle to use is this angle right here, theta. So that's the angle that I'm going to use. Okay. Now, that's not the only angle you could use. You could also use this angle, say, or you could even use this angle. But the most convenient angle to use is this acute angle inside the triangle that we've drawn. Now I know that ux is negative 4 units. And uy is plus 7 units. So we need to figure out the magnitude, the length of the hypotenuse, and this angle. I'm going to do the direction first because people tend to forget the direction if they don't do it first. So I'll do the direction first, which means finding this angle. So for that, we're going to use SOHCAHTOA. Now, should I use sine, cosine, or tangent? Well, notice that I don't know the length of the hypotenuse yet. So since I don't know the length of the hypotenuse yet, sine and cosine are not too useful right now. On the other hand, I do know both the adjacent side. Let's make a note here that we're focusing on this angle of theta. We could focus on this angle at the top, but it's more common to focus on the angle at the tail of the overall vector. Well, I know this adjacent side. This side is adjacent to theta. And I know this opposite side. This side is opposite to theta, but I don't know the hypotenuse. So it's most convenient here to use the tangent. And we can say the tangent of the theta is the opposite side over adjacent, TOA. What do I plug in for theta? Well, I just keep writing theta because I don't know what theta is. That's what I'm trying to figure out. And for the opposite side, well, I'm going to plug in 7. And for the adjacent side, 4. Now, notice I didn't include this negative sign because what does this really stand for? What this stands for is the length of the adjacent side, and lengths are always positive. And similarly, this is the length of the opposite side, and lengths are always positive. So what we're really using here is we're really using the magnitudes. In fact, maybe just this one time, I'll put in one more little step and show that the length of the opposite side is the magnitude of uy, and the length of the adjacent side is the magnitude of ux. So we can put those in. and therefore those magnitudes are 7 and 4. So again, we don't put in a -4 here because what we're dealing with is lengths. Now, do you know how to solve for theta? If you watched my earlier video on, or video series on SOHCAHTOA, I talked about how to solve for theta in this case. So what we need to do is use inverse tangent. So this is the input to the tangent, and this is the output, and we need to kind of get them to trade places. So we take the inverse tangent, and with the inverse tangent, we take this output. The output of 7/4 becomes the input for the inverse tangent. And the input for the regular tangent becomes the output for the inverse tangent. And now we've solved for theta. I went over this method in more detail in my videos on SOHCAHTOA, so you should watch those earlier videos if that was difficult algebra for you. Now we can use our calculator. If you're not allowed to use a calculator, if you're doing a test where you can't use a calculator, you could just say the angle is inverse tangent of 7/4. You could just say the angle is inverse tangent of 7/4. But if we can use our calculator, so do you know how to find inverse tangent? Here's inverse tangent on this calculator. It's the blue above the key, so I use my second key to get that blue function, inverse tangent of 7/4. Should probably check again to make sure we're in degrees mode. So that ends up being 60.3. Now, what are the units on this? Well, we expect theta to be an angle, and we expect the angle to be in degrees. Again, remember, we know this is in degrees because we check that the calculator is in degrees mode. So this angle would be 60.3 degrees, and we can build that into our triangle. Okay, so that shows how we can use inverse tangent to find this angle, this direction. Now we also need to know the hypotenuse so we can find the magnitude. Now there's a couple different ways we could do that. We could now use SOHCAHTOA. We could now use SOHCAHTOA to find this hypotenuse, but it's more conventional to do what? To use the Pythagorean theorem. So I'll use the Pythagorean theorem here. So our Pythagorean theorem here would tell us that the length of ux squared plus the magnitude of uy squared is going to be equal to the overall magnitude squared. Here I'm using the symbol for magnitude. And so then we could say that that means that the square root of ux squared plus uy squared is the square root of u squared. We're going to take the positive square root because we want a magnitude, and a magnitude can't be negative, and this symbol by default means the positive square root. So that's going to be 4 squared plus 7 squared. Now, in this case, it wouldn't be a disaster if you included the negative sign. Even if you included the negative sign, it wouldn't matter because when it gets squared, the negative sign would disappear. Nevertheless, technically what we're using here are lengths. So I used the symbol for magnitudes to show that the Pythagorean theorem is about lengths, and lengths are never negative. All right, and then we can work this out in our calculator. You can actually do this in one step on your calculator. But if you want to do it on one step on your calculator, if your calculator has a square root template, it's easy to do it in one step. But if you're using a non-fancy calculator that has no square root template, you need to put in this parenthesis so the calculator knows that the whole thing is inside the square root. And then we do 4 squared plus 7 squared. My calculator happens to put the parenthesis in automatically. But you would have to put the parenthesis in yourself if your calculator doesn't, unless you have a square root template. All right, so that gives me this. So I can do this all in one step. And I get that U is 8.1 units. By the way, just a little detail here. So I showed you how you can do this on one step on your calculator if you're not using a very fancy calculator. If you're using a fancy calculator, I'll put my calculator in fancy mode. When the calculator's in fancy mode, it's even easier because in fancy mode, my calculator has a square root template. And then we can do 4 squared. And notice now you don't need, whoops, that didn't come out right. But now you don't need the parentheses. Now you don't need the parentheses because the calculator's square root template clearly shows that all of these things are in the square root. And hopefully we'll get the same answer. Yes. But anyway, the point is that with a square root template, you don't need the parentheses. And again, if you're using a calculator that doesn't have a square root template, then in that case, you do need the parentheses to show where the square root starts and stops. Okay. If you want to do this calculation in one step rather than breaking it up into a bunch of steps, which is what a lot of students tend to do. All right, so then we can say this hypotenuse has a length of 8.1 units. Now, remember that when we obtain a result in physics, it's always good to pause and ask if there's a way to check whether our result is correct or makes sense. Is there any way to check our results here? Well, yes, we can use the idea that we talked about in the first video. These ideas, which I hope you remember from the first video. The longest side of a right triangle is the hypotenuse, so we can use that to check our results. Here's the value that we got, and you can see that this did come out to be the longest side of the triangle. 8.1 is bigger than 7 or 4. If this answer had come out to be something like 6.2, if this had come out to be 6.2 for the hypotenuse, we would have known we made a mistake, because that would be less than 7. All right, so that's one way we can check that these results make sense. This number came out to be bigger than either of the two components. And the other thing we can use is that a longer side should be opposite a bigger angle. Now, we haven't figured out the angle at the top of the triangle, but I hope it's obvious to you that this angle is smaller than the 60.3, because we know they add up to 90. Since we know they add up to 90, it should be obvious even without calculating the angle at the top that this angle at the bottom is the bigger angle, bigger than 45 degrees. And it should be obvious that this angle at the top is the smaller angle, smaller than 45 degrees. And yes, this bigger angle is opposite the bigger side of 7. And this smaller angle is opposite the smaller side of 4. So this did check out. The longer side, 7, was opposite the bigger angle, 60.3. And the shorter side, 4, was opposite the smaller angle. Whatever this angle is, we know it's less than 60.3, less than 45 degrees, in fact, since these two angles have to add up to 90. So that's another good way to check that we did this correctly. Those are pretty easy checks to make, so I encourage you to get into the habit of always making these checks when you have numerical results and you're working with components. Anytime you're trying to break a vector into components or use the components to figure out the overall vector, and if you're working with numerical values, you should always be able to use these ideas to check whether your results make sense. Now we're ready to fill in our table. So the magnitude of the overall vector is 8.1 units. And we figured out that the arrow for the overall vector points kind of like this. And the direction of the overall vector is at an angle of 60.3 degrees as shown. Now, you need to include your picture then. All right, I can build that into the picture right here. So I can say this is 60.3 you need to include the angle in your picture, because otherwise the reader wouldn't know where the angle is. For all they know, you might mean that there is an angle, that the angle of 60.3 is an angle like this, or the angle of 60.3. Without the picture, it wouldn't be clear where the 60.3 is. So when you're describing the direction of the overall vector by an angle, the easiest way to do that is to say what the angle is, but also to provide a picture that shows where the angle is located. And then we can say the overall vector. That, to specify the overall vector, we need a magnitude and a direction. So that was 8.1 units at an angle of 60.3 degrees, as shown in the picture. Okay, so now we've accomplished what we wanted to learn how to do. We've learned how to take the components and figure out the overall vector. Now, I went through that very slowly, trying to really describe all the details, but I hope that you can see with practice, you can learn to do that pretty quickly. You want to get to the point again where this is a boringly easy part of the problem. So I took a long time here because I wanted to be as clear as possible, but you want to keep practicing this until it doesn't take you that long and until it's boringly easy. So I hope you can see now that what we've learned is, in that last example, we were given the components and we used that to figure out the magnitude and direction of the overall vector. We went from here to here. For that, we used the inverse tangent function. We used inverse tangent rather than inverse sine or inverse cosine because to begin with we didn't know the hypotenuse. So it was most convenient to use tangent since that didn't require us to know information about the hypotenuse, which we didn't know yet. So we saw here how we could use the inverse trig function and also the Pythagorean theorem. Another important thing here is that we did not include the negative sign on this -4. If we had included that negative sign, that could have led to confusion in our solution. SOHCAHTOA is about lengths, and lengths are always positive. Also, we saw how do you describe the direction of the overall vector? You describe the overall vector, you describe the direction of the overall vector usually in terms of an angle. We usually describe the direction of the overall vector in terms of an angle. We can describe the directions of the components just with a plus or a minus, but we can't just use a plus or a minus for the overall vector. In fact, notice we didn't use plus or minus at all for the overall vector. Instead, we specified its direction using an angle. Please pause the video and try this problem. Okay, I hope you tried the problem, and I hope you thought it was boringly easy. If you're not there yet, that means you just need to keep practicing until these problems are boringly easy. And now let's go through the boringly easy, hopefully, solution. So Vx here is plus 3 meters per second. And again, even though the problem didn't include the plus sign, it's a good idea for a beginner to include a plus sign in front of positive components, because that tells us, emphasizes that the direction has a meaning. This component is towards the right, and Vy would be -5 meters per second, and that's our downward direction. So then our arrows would point to the right and down. Right and down, and our magnitudes 3 meters per second and 5 meters per second. Now remember that on real problems, you're usually not going to have to figure out every single one of these labels. But we're figuring out every single one of these labels right now just for practice. We have seen that it is useful when you're solving problems to have separate symbols for the component and for the magnitude of the component. So it's helpful to practice those. Now we need to figure out the overall vector. Now again, a naive student might think that they could just add 3 plus 5 to get 8, or maybe add 3 plus -5 to get -2. But when the vectors are pointing in neither parallel nor anti-parallel directions, you can't just add or subtract the components to find the overall magnitude. By the way, I guess I should have emphasized that here. Notice that 8.1 is not 7.4, and 8.1 is also not 7 minus 4. you don't just add or subtract these two numbers to find this number. Instead, you have to use the Pythagorean theorem. So let's try to write the overall vector. Well, we can start by drawing Vx to the right, and then Vy down. Those are supposed to be horizontal and vertical lines. And this line, I'm not going to get this exact proportional again, but this line should at least be longer than this line. This will be our -5. So the overall vector starts here at the tail of this component and ends over here at the head of this component. So I put this arrowhead at this component head and this arrow tail at this component tail. So this will be our overall vector v. And to find the direction, we could find this angle, but it's more conventional to find the angle here at the tail. There's other angles we could find. We could find this angle instead, or we could find this angle. But the easiest and most conventional angle to find here is the acute angle at the tail of the overall vector. So that's the one we're going to try to find. So this will be our hypotenuse. This is the angle that we chose to focus on. Remember that on this problem, we chose which angle to focus on. If you wanted to, you could focus on this angle, but instead I'm going to focus on this one. Then we could say this side is adjacent to the angle theta we're focusing on, and this side is opposite. Notice that we made up the symbol theta here. The problem never mentioned the symbol theta. We made up that symbol just because it's going to be useful to us in finding a way to specify the direction. And then we're going to use SOHCAHTOA. We could start by finding either the magnitude or direction. I'm going to do the direction first, because otherwise people might forget the direction if they do the magnitude first. So far, we don't know the hypotenuse. So sine and cosine are not too helpful yet. So now I'm going to use the tangent, which doesn't require us to know the hypotenuse. Tangent theta TOA equals opposite over adjacent. And remember, the opposite really means the length of the Vy side over the length of the Vx side here. So I'll show that I'm using magnitudes. So that would be Vy magnitude, which is 5, over Vx magnitude, which is 3. If you watched my video on the unit circle, you know that sine and cosine can never be bigger than 1. But tangent definitely can be bigger than 1. Again, I talked about that in my video on the unit circle. So if you had a sine or a cosine that was bigger than 1, you would be making a mistake. But it's perfectly okay to have a tangent that's bigger than 1, which we have here. So this is fine. Notice we're not putting in the negative sign because this is about lengths. All right, and now we need the input and the output to switch places, so to speak, because we want to solve for this input. So we use the inverse tangent function to do that. And when we go from tangent to inverse tangent, the input of tangent becomes the output of the inverse tangent, and the output of the tangent becomes the input of the inverse tangent. If you are not allowed to use a calculator, you could just use this as your answer for the direction, but with our calculator, we'll do inverse tangent 5/3. Now that's an angle, so it's going to be in degrees. Theta equals 59 degrees. We can build that into our picture. Now, how do we find this magnitude? Now we could use sine or cosine to find this magnitude, but we'll do it the conventional way and use the Pythagorean theorem. So that would tell us that the magnitude of Vx squared plus the magnitude of Vy squared equals the magnitude of the overall vector squared. So Vx was 3 and Vy was 5. And I'll do this in the non-fancy mode without the square root template. So we need a parentheses, which my calculator puts in automatically, if we want to do this in one step. See, notice how the parentheses tell the calculator that everything here is inside the square root. How can you check if that answer makes sense? It makes sense because we expect the hypotenuse to be longer than the legs. If this number had come out to be less than 5, we would know that we made a mistake somewhere. Remember to include units on your answers here, meters and degrees. After I finished recording for this problem, I realized that I made a mistake. Did you notice my mistake? I'm always saying we have to be very careful with the units, but I was not careful enough here. The units for the components here are meters per second, and therefore this result should have come out to be meters per second. Did you catch that? So again, this should be meters per second too. So that was a mistake that I made in the initial recording of this video. So as you watch the remainder of the explanation for this video, unfortunately that will continue to have those mistaken units. But the units here should not be meters, they should be meters per second, since the components were in meters per second, and of course those are the correct SI units for velocity. Well, remember that now that we have some results, we should see if we can check these results to see if they make sense. Remember how to do that? We can use these ideas that we've talked about a few times now. The longest side of the right triangle should be the hypotenuse. Well, that does match our results. This value is bigger than either of the two legs. If this value had come out to be shorter than either of the legs, we would have known we made a mistake. So that checks out. And we can also use this idea. The longer side should be opposite the bigger angle. In order for that, we need to ask which is bigger, the acute angle here or this acute angle. And that should be obvious without having to do any calculations, because remember the two acute angles should add up to 90. So since this angle is bigger than 45, it should be obvious that this acute angle has to be less than 45. So the two angles can add up to 90. So it should be clear that this angle at the top is the bigger of the acute angles. And this angle at the bottom is the smaller of the two acute angles. And is the bigger angle opposite the longer side? Let's see. So here's the bigger angle, and it's opposite a side of length 5. Here's the smaller angle, and it's opposite a side of length 3. So yes, the larger angle is opposite the larger leg of 5. Smaller angle is opposite smaller leg of 3. Notice here we're just comparing the two legs, not the hypotenuse. So that also matches up. If the longer leg had not been opposite the bigger angle, we would have known we made a mistake. So again, we see that whenever we're working with these types of problems involving components, we can always check numerical answers to see if they make sense using these two ideas. Now, of course, those checks are much easier if you've built your results into your right triangle. So I encourage you to always build your results into your right triangle. One advantage of that is it makes it easier to check if the results are making sense. And now we can build that all up into our sketch. So we decided that the overall magnitude here was 5.8 meters, and our overall vector looked kind of like this, and it's at an angle of 59 degrees. And again, this is meaningless unless you include a picture that shows where the angle is. Is this an angle with the horizontal, with the vertical? Is it to the left of the, below the horizontal, above the horizontal? You need to draw a picture to show where that 59-degree angle is. And now the reader knows exactly what you mean by the direction of this. This is supposed to be a straight line. So we can say the overall vector had a magnitude of 5.8 meters at a 59-degree angle, as shown in our picture. All right, so once again, we have successfully been given the information for the components, and we figured out the overall vector. I hope that was a real boring explanation for you. If this is boring, then you're accomplishing your goal. You want to get to the point where this information is boringly easy. And we're also just getting practice with vector notation. By filling in all these different notations, you're just getting practice with the difference between an overall vector and the components, and the difference between directions and magnitudes. Okay, and I'll mention again that the first time I recorded this explanation, I made a mistake with the units. So let's go through and fix those to get those correct. Hopefully you are mentally correcting those all the time. All these units should be not meters, but meters per second. Since we started with components in meters per second, we should get an overall vector that uses units of meters per second as well. So now we're using the correct units. Please try this. Well, we're given the components, so we can start by writing the components. Vx is negative k, and Vy is plus q. Remember, for a beginner, it's best to put a positive sign in front of positive components, even if the problem doesn't do that. What's the value of putting in this plus sign? Well, that reminds us of the importance of the direction of this component, which is up. And this component is in the negative x direction, which is left. By the way, notice that we would not include units here. You might know the units for velocity are meters per second, but we don't include units because the units are thought of as being included in the symbols. The units are inside the symbols, so to speak, so it would be double counting, so to speak, to write them outside the symbol as well. I talked about that issue in an earlier video. So the Vx arrow here would be to the left, and the Vy arrow would be up. And then this magnitude would be k, and this magnitude would be q. For the magnitudes, we leave out the signs. Now we want to draw the overall vector. So our Vx arrow is to the left. Then our Vy arrow is up. There's not really enough information here to know which leg should be longer. We weren't given enough information in the problem to know which leg is longer, so you can draw it however you like. We know Vx is negative k, and Vy is plus q, and then the overall vector starts over here. And I'll do the best I can to draw a straight line that ends over here. And the head of this overall vector is where the head of the component is, and the tail of this overall vector is where the tail of the component is. And we'll try to find this angle theta. The problem didn't give us that symbol theta, we just made it up. So we have a symbol for the angle that represents the direction. If you wanted to, you could find the angle at the top of the triangle, but it's more conventional to find the angle at the tail of the overall vector. So this is the angle I'm going to focus on. And therefore this side is adjacent to the angle we're focusing on. This side is opposite to that, and this is the hypotenuse. So far we don't know the hypotenuse yet, so I'm going to use tangent, which doesn't require us to use the hypotenuse. Tangent of theta is opposite over adjacent. If you write this, you messed up. You have to tangent, sine, cosine, tangent always have to have an input, which is an angle. We don't know what theta is, so I'll just keep writing it as theta. Now our opposite side here is the length, the magnitude of the Vy side. And the adjacent side is the magnitude of Vx. So this magnitude is q, this magnitude is k, we don't include the negative sign because here we're using just something that represents the length. And again, remember, what are we trying to solve for? Q, K, or theta? Well, in this problem, Q and K are the givens. We probably should have made a note of that. Q and K are the givens on this problem because those are the symbols that were mentioned in the original problem. So theta is the unknown, and to find that unknown, we'll use inverse tangent. So theta will be the inverse tangent of Q over K. So this will be inverse tangent of Q over K. Then we can use the Pythagorean theorem to find this side. Okay, so then we have that this hypotenuse is square root of K squared plus Q squared. Notice I don't say V equals this. I use a comma because remember, this is only the magnitude of V with the arrow. We can say that V without the arrow is equal to the square root of K squared plus Q squared. And our arrow, all we know about this arrow is that it points up and to the left. And then our direction is at an angle inverse tangent Q over K. And we have to show in our picture where that angle is. So that angle is here. Inverse tangent Q over K. You have to show in your picture where the angle is so that the reader knows what you're talking about. So then we have a direction, which is at a magnitude of root K squared plus Q squared at the angle given by the inverse tangent. Okay, again, I hope that was pretty easy for you, but here we had practice with a no number problem, how to figure out the overall vector when you're not given any numbers. That's a skill you'll probably need in your class. Remember, our givens were Q and K, so all the answers should be only in terms of Q and K, and I think I did that. Every single answer here boils down to some combination of Q and K. For example, you can't just say the angle is theta, since theta is a symbol we made up. You could only say the angle was theta if you said who theta was, inverse tangent of q over k. Please pause the video and try this problem. So here we're given the components. Make sure you notice which component is which. Our AY component here is -8. And our AX component is 0. And AY is -8 meters per second, which is the same thing as -8 meters per second squared. So the directions of the y component is in the negative direction, which is down, and a 0 component has no direction and no arrow and 0 magnitude. And this arrow points down and has a magnitude of 8 meters per second squared. Okay, and this should be pretty easy to find the overall vector. If one of the components is 0, then the overall vector is the same as the non-zero component. The overall vector here has the same magnitude and direction, as the component. The overall vector has the same magnitude and direction as the component. So I'm trying to draw this down, and I'm trying to draw it about the same length as this arrow here as best I can. So then this magnitude would be 8 meters per second, and this direction would be down. Now, one tricky part is we don't want to say, even though this is kind of the same as the component, we don't want to say this is -8, because we don't use signs to represent the directions for the overall vector. We don't use a sign to represent the direction of the overall vector. Instead, we specify it with a magnitude, which is 8 meters per second. Normally, we would specify the direction of the overall vector with an angle. But for this very simple vector, we can specify the direction with a word, down. So you can see the overall vector is basically identical to the component. The only difference is that we specify the direction of the component with a minus sign, but we don't use a minus sign to specify the direction of the overall vector. Instead, we use the word down. So we've been discussing that the direction of a vector component can be represented by a plus or minus sign, as we do here. But the direction of the overall vector should not be represented by a plus or minus sign. No plus or minus sign here. But why don't we pause to explain why that is? Why can't we? Why can't we just say that the overall vector is -8? Like we said, the y component was -8. Well, I'll explain the logic, because that might help you to remember the rule. So it's okay to put the negative sign here. How would a person interpret this negative sign? Well, a person would say to themselves, this component is pointing in the negative direction. Now, does this mean the negative x direction or the negative y direction? Well, clearly it means the negative y direction because it's a y component. So a person would know to interpret this negative sign as the negative y direction, not the negative x direction, because they know they're dealing with a y component. But do you see that logic wouldn't work for the overall vector? Somebody who read this notation would not know how to interpret the negative sign. Someone who looked at this notation wouldn't know whether this means the negative x direction or the negative y direction. The overall vector is not tied to any particular axis. Obviously, the y component is tied to the y-axis, but the overall vector doesn't make direct reference to any particular axis, so this is a bad notation, because if a reader saw this negative sign, they wouldn't know whether this means that the overall vector is pointing in the negative x direction or the negative y direction. That's the reason why it's good to use plus and minus signs to represent directions for components, but it's wrong and unhelpful to use plus and minus signs to represent the directions for overall vectors. Instead, we have to represent the direction of an overall vector with an angle, or, as in this case, by a word. such as down. That way, any reader could look at this information and know from this information what the actual direction of the overall vector was. Okay, so you should keep in mind that we will represent directions of vector components by plus and minus signs, and you should keep in mind that we do not represent the direction of the overall vector by a plus or minus sign, and now you should know why. Now you should understand why we don't use plus or minus signs for the overall vector, and hopefully that will make it easier for you to remember these rules. All right, well, I hope that was definitely a very boring and easy problem for you. Just remember that if one of the components is 0, then the magnitude of the overall vector is the same as the magnitude of the non-zero component, and the direction of the overall vector is the same as the direction of the non-zero component. And this is how we would use our symbols in this case. Notice that when there's a 0 component, you don't try to draw a right triangle. If you try to draw a right triangle, you'd probably end up confusing yourself here. We don't draw a right triangle. We don't need the Pythagorean theorem. We don't need inverse tangent. When one of the components is 0, we have a very much simplified method for figuring out the overall vector, because again, the overall vector is basically identical to the non-zero component. Okay, and to wrap up this problem, did you notice I made another mistake on the units? So I hope that you're making a strong effort to pay attention to the units. That's an important habit. And again, it looks like I could use some work on that habit too. These units came out incorrectly, didn't they? To be consistent with the units I used everywhere else, this should be meters per second per second. So that was a careless mistake on my part. But our aim should really be to pay close attention to the units and try to avoid those careless mistakes. So I hope you didn't find that to be confusing, but these should be the correct units for that row. Please pause the video and try this problem. Okay, well, this is should be a super easy question. I'm just covering this for completeness. Here we have that both components are 0, so it should be very easy to fill out this table. Both of the components are 0. That means that each of them has no direction and no arrow. And the magnitude of each component is 0. And I hope it was apparent to you that that means that the magnitude of the overall vector is 0. And therefore the overall vector has no direction and no arrow. So we can say that our overall vector A has magnitude 0 and no direction. 0 vectors have no direction. That should have been super easy. I just wanted to cover the case of a vector that has 2 0 components, just for completeness. But it's not like this is a weird or unusual case. You will certainly see plenty of problems in your physics class where both components of the acceleration are 0. And if you see a problem where both components of the acceleration are 0, that would tell you that the overall acceleration is also has a magnitude of 0 and no direction. That very easy case. Well, one lesson we get from this easy problem is that a 0 vector has no vector arrow. When the overall magnitude is 0, there's no vector arrow. We don't try to draw an arrow to represent a vector whose overall magnitude is 0. The length of the vector arrow is supposed to represent the magnitude. So it should make sense that if you have 0 magnitude, that would be an arrow of 0 length. But an arrow of 0 length is just another way of saying no arrow at all. So in this case, with the 0 vector, there's no arrow to be drawn to represent the vector. That doesn't mean the vector doesn't exist. The vector exists and it has a magnitude of 0. We just don't draw an arrow to represent it. Okay, so I hope you feel now that you have a strong command of these two key skills. I hope you feel that anytime you're given the magnitude and direction of the overall vector, you can figure out the vector components. And what we covered in this video is I hope you feel that anytime you're given the vector components, you can figure out the magnitude and direction of the overall vector. Now that I hope you have the basic skills down, in the next couple of videos we'll try to cover some more difficult and some more challenging applications of these concepts and skills involving vector components. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge of $1 or more at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.